In this video, I'd like to continue talking about constructing sinusoidal functions by looking at one final example problem. And in this problem, we are given information about our sinusoidal function, namely that it intersects the midline at 0, -6, and then has a minimum point at 2.5, comma, -9. And right away, since we know the midline point, we can figure out the equation for that midline, since that's just equal to the y value, namely that y is equal to -6. But let's start by plotting that point. We have at an x value of 0 that the function goes through at -6. And we can also just draw in that midline, and we can use that as a guide to actually graph our function. So this has the equation y is equal to -6. And then the function is going to go through a minimum point at 2.5, comma, -9. So we need to determine what scale to use for x here. And we can just use a scale of 1, just like we use for the y values. So if you want, you can mark this in. This is 1, 2, 3, and so on. And same for our y values. So at 2.5, we are down at -9 here. So 2.5, we go 1, 2, 3 below that line of -6, meaning we are roughly right here. And we could visualize what our curve actually looks like. Since this is a minimum, it will come back up to the midline, then go to a maximum, and then come back down to the midline again. But to actually figure that out, we need a little bit more information here. So let me label this point. This is at 2.5, comma, -9, and this one's at 0, -6. Now, we need the general equation for a sinusoidal function, and we need to determine whether or not to use the sine or the cosine. We could, in theory, use both, but one of them will generally be easier to use. And we just need to remember the parent functions of both sine and cosine. And for the cosine, remember that its parent function goes through at a maximum value and then comes down to a midline value at pi/2 radians, which would be somewhere in here, and then comes down to a minimum value at pi radians, but it will look something like that. And we can see that for our function, it's intersecting the midline when x is equal to 0, not its maximum value. So the cosine doesn't make as much sense here because the sine function goes through the midline or the origin when x is equal to 0 for its parent function. And then after that, we'll come up to a maximum value and then go down to the midline again and carry on like that. That would be the sine function, parent function. And since our function here is going through the midline, it makes most sense to use the sine parent function rather than the cosine. Though, like I mentioned, if you want, you can use the cosine and then just shift it horizontally. And we also need the general sinusoidal equation that y is equal to a multiplied by the sine or the cosine of bx plus c plus d, where a affects the amplitude, b affects the period, c affects whether or not it shifts left or right, and d will shift the function up or down. And we can figure out what d and a are fairly quickly, since we know we shifted the parent function down 6 units. So d would just be -6. D is always equal to the equation of the midline. And then a, like I mentioned, affects the amplitude. We know that the absolute value of a is equal to the amplitude. And the amplitude in this case is the distance from the midline to a maximum or minimum, and we can see that that distance is simply equal to 3. So we know that the absolute value of a is equal to 3. And to determine if a is positive or negative, we just need to consider whether or not we have a reflection. And in this case, we do have a reflection, since the sine function goes through the midline and then comes up to a maximum point in terms of its parent function, and then comes back down again. But we can see with our curve that we go through the midline and then come down to a minimum point. So when we make a negative, let me draw this in a little bit more carefully. When we make a negative compared to our parent function, it just reflects it across that midline. And it looks like we do have that reflection here. So in our case, a is -3. And we can also see that we have no horizontal shifting, since just like the parent function, it goes through the midline when x is equal to 0. So c is 0. And lastly, we can figure out the period. Since we know the formula for the period is 2 pi over the absolute value of b. So if we can figure out the period, then we can solve for b. And the period, remember, would be one unique oscillation on this sinusoidal function. So if we carried out the curve, we can kind of imagine what it will look like. It will go up to its midline, that's half a period, and then come back down. After going to its maximum, it will come back down to its midline again, and this would be one period. But there is nice symmetry with the period, namely that if we go from one midline to the minimum and then back up to the midline, this is half a period. And if we just go from a midline intersection point to either a maximum or minimum, that would be 1/4 of the period. So this horizontal distance here is 1/4 of the period. So if we can figure out what that is, we can just multiply it by 4 to figure out that period. So let's write that our period is really 4 times this horizontal distance. And this distance, going from 0 to 2.5, is just 2.5. So our period in this case is equal to 10. And we can use our formula now to determine b, since we know that 10 is 2 pi over the absolute value of b. And if we multiply each side by the absolute value of b and divide by 10, we have 2 pi over 10, which simplifies to pi over 5. So we figured out at least the absolute value of b. Now, to determine if b is positive or negative, we just need to remember what happens when b is negative. So let's consider that parent function again. We know it looks something like that, very roughly. If the inside was negative, if this was negative x, that would just cause a reflection about this y-axis. So it would look something like that. And if we carried it out, it would continue looking like that. But remember that we already considered that reflection by making a negative. So when you have the sine function, if both a and b are negative, they will actually cancel each other out with those reflections, and you just get back the normal shape compared to the parent function. If one of those is negative, then you do get that reflection, and that reflection looks the same in both cases, though technically it is a little bit different. When a is negative, it reflects about the x-axis, and when b is negative, it reflects about the y-axis. But with sinusoidal functions that haven't been shifted, they actually look the same, whether or not a or b is negative. But we only have one reflection here. If we made b negative, it would actually reflect this back up, so that we get back the shape of our parent function. But since we only have one reflection, only one of these needs to be negative, and we already made a negative, so b can be a positive number. We can conclude that b is just pi over 5. Though, like I mentioned, if we want to switch these, that would be perfectly valid as well. So at this point, we have all of the information we need for our function. We can write in the equation that f of x is equal to -3 multiplied by the sine of b times x, or pi over 5 times by x plus 0 and minus 6. And of course, we can test this using a graphing calculator or something like Desmos. And when we plot this, we just need to make sure that these two coordinates are actually on our curve. And like I mentioned, if you want to make this positive and this negative, I encourage you to plot that as well and see for yourself that it is actually the exact same curve.